Hello students, welcome back. Previously we discussed what is a random variable and then went through some examples, and then finally we discussed what is so-called discrete probability distribution. I have a nice explanation, yes, to a certain degree. However, that explanation brought about two more questions. What is probability mass function? And what is cumulative distribution function? Without answering those two questions, I have to say the explanation and discrete probability distribution is still imperfect. So let's go ahead and answer those two questions. What is the probability mass function? Let's answer it using this example problem. An urn contains 5 red balls, 3 green balls, and 2 blue balls. And we have these 3 random variables, x, y, and z. And then let me show you the probability mass function. The definition is pretty simple. It's here. The probability that the random variable x taking small x value. And here, I'm not going to use p because I have 3 characters, capital X, capital Y, capital Z. So instead of PQR or P1, P2, P3, I'm using small f, small g, small h. Previously, I used small p, but I'm just using f. Other than that, no difference there. So, f of x is, by definition, probability of capital X equals to x, alright? Now, capital X can take x value equal to 0, that corresponds to red, or 2, which corresponds to green, or 3, which corresponds to blue. Otherwise, it's impossible, because that sample space has only 3 colors. And those 3 colors correspond to 0, 2, and 3. So those are possible numbers. So those are possible small x values, otherwise impossible. Therefore, I can summarize like this. The probability is 5/10 for x equals to 0, 3/10 for x equals to 2, and 2/10 for x equals to 3, which correspond to colors R, G, B respectively. And finally, 0, probability 0, or in other words, impossible for any other color or any other x value. You can write like this as small x and f of x, which is more typical, or sometimes you can write capital X and capital P of x. This one is a little bit less typical. This is usual case. Small x value, the real value that's you can take, and then f of x is the name of the mass function in this case. I could have used different characters. I could have used p, or I could have used q, or whatever. I didn't want to use q, and I can make confusion with something else, or even less. Now, this is not the only form. You can use vertical tabular form too if you want to. X is either 0, 2, or 3. We get probability 5/10, 3/10, 2/10. Otherwise, probability is 0. Now, which tabular form do you prefer? Horizontal form or vertical form? Well, to me, it's push. And our textbook uses this one more often. And let me see, what did WebWork do? I think it used this one a bit more often, but it's tabular form. Now, you can express this in piecewise defined function form as well. So, if condition, 0, 2, 3 respectively, and then of course otherwise. In otherwise, probability is always 0, so many people just skip this part, and that's okay to me. Alright, and then in either case, here's a graph form. You can express it as dots. red dot corresponds to red, green dot corresponds to green, blue dot corresponds to blue, and they are 0, 2, and 3 respectively, you see? So random variable assigned 0, 2, and 3 for RGB, otherwise nothing, and then there were nothing else. So all other probabilities are 0, so you see everything down here except these 3. That's one way to express this in graphic form. Another way is to use something called probability histogram. Instead of those dots, put some rectangles there, but the key here for these rectangles is they have to have same width and they should not be overlapping. Which do I prefer? Personally, I prefer these dots. But this one is also a widely accepted expression. Now, how about this? Negative 1.5, 0.5, or 1. Those are only the possible outcomes here because they came from the sample space RGB. So otherwise, probability is all 0. Therefore, we get this kind of tabular form. Probability 5/10, 3/10, 2/10 for negative 1.5, 0.5, and 1.0 respectively. Otherwise, probability mass is 0. Probability 0 means impossible. And then you can use random variable capital Y and probability of this capital Y. You can use this expression too if you want to, but this one is a little bit more customary. X value is a real value, and then this is just the name of that function. Previously I used f of x, now I'm using g of x to avoid confusion. That's it. You can use this horizontal tabular form or vertical tabular form. The same, aren't they? So x values are these, and then probability values are those, respectively, and then otherwise all 0. Oh, one further comment. These are all probabilities, so they have to add up to 1, right? Probability of anything that's possible put together, and then you have to get 1, right? The probability of entire sample space. Another way is to use piecewise defined form. And if, and then we have probability values and 0 otherwise, and a lot of people skip this 0 otherwise. Same goes here. This part, that part, this part, many people just skip that. Now, how about graph? Negative 1.5 is a possibility, and there the probability is 0.5. And 0.5 is a possibility, so x equals to 0.5, and that probability is 0.3. And x equals 1 is a possibility, and that probability is 0.2. Otherwise impossible, so all this on the x-axis. Another way to express the same thing is to use probability histogram. We use 3 rectangles like this with the same width and no overlap. Now, how about the third one here? In this case, you can have only 2 possible values, negative 1.25 or 4.75, nothing else. As far as this random variable z is concerned, there's no distinction between r and g. So we have this tabular form, 1/10 versus 2/10. Those are probabilities. And red or green, no distinction there, so I just use brown here for negative 1.25. And that. Make sense? And the probabilities always add up to 1. Piecewise defined function form. And then the graph form. You have only 2 dots because you have only 2 possible outcomes. Negative 1.25 here, and that probability is 1/10, so the height goes to 1/10. And 4.75 is here, that height goes to 2/10 because that's the probability. And then you can use probability histogram. Here I decided to put both histogram and dots together. And okay, this one I do like. If I see just rectangle, I don't know. I generally prefer these dots. But in the probability histograms, if I see dots as well, okay, I feel better. But there are some cases probability histograms are more convenient, to tell the truth. So that's why I introduced that to you. So those kind of things are called the probability mass function. And, this kind of tabular form, that's the mass function. Now, what do you do to this mass function? Okay, before going over to other examples, let me show you the use of mass function. No, not this one. Expected value. So payoff times the probability and add them all up, and that's called the expected value. For example, let's see, is that the same game you had before? Yeah, 0, 2, or 3. Yeah, I think so. And then what's the expected value? Let me see. Where is this? Probability mass function. Let me just copy and paste that thing here. Okay, this is for x. And then 0, 2, 3 are possible outcomes, otherwise impossible, so don't worry about it. And that probability is 5/10, 3/10, 2/10 respectively. So multiply by 5/10, multiply by 3/10, multiply by 2/10, and add them all up, and that is the expected value. So what does that mean? And on the average, you're expecting to win $20 or so if you keep playing this game X. It doesn't mean in your next play you will earn $20. That's not possible. But that's the best prediction, and give or take, you're going to get something. And then, for example, this is the expected value for this game. And then in order to play this game, you have to pay $1.50 each time. Then as a matter of fact, your expected loss is 3 cents, 30 cents, you see, each time you play the game, because the expected value is $20. And, the payment you have to pay to play the game is $50. Then, roughly speaking, each time you're losing 30 cents. In terms of, best statistical prediction. And then, of course, nothing is accurate in statistics, so sometimes you earn more, sometimes you lose more, but overall, that's what you expect. And that's how casinos make money all the time, basically. They charge a little bit more than expected value. So that was an example of the probability mass function, expected value. And once you have the probability mass function, it's easy to calculate the expected value. We're going to talk more about the expected value in a separate video, but for now, let's focus upon the mass function. Alright, so much for mass function, and then let's discuss cumulative distribution function. Same game, and this time cumulative. Alright, cumulative. So the possible values are x is equal to 0, 2, or 3 in this case. So there goes a mass function. PMF, probability mass function. And in alternative expressions like this. And then graphs are like that, either dot plot, which I prefer, or probability histogram, acceptable. Now let's consider cumulative distribution function. So cumulative distribution function is like this. So probability that random variable x takes a value less than or equal to x. And the best way to visualize that is to look at the number line, and possible x values are 0, 2, and 3 respectively. Otherwise, probability is 0. Okay. Now, to have x less than 0, then probability of getting anything less than 0, that's impossible, isn't it? You see, the smallest possible value is 0. So anything less than 0, that's impossible. So always, this probability over here is 0. Always I begin from 0. And then now, from 0 to 2, something takes place. We have a jump because, you see, x is less than, say, 0.1, then x is selected over here, then it includes 0, you see. Red is now possible, or 0.1, or 0.2, which is around here, or all the way up to 1.999, which is around here. We have only one possibility, this red dot, and that takes place, and that probability is 5/10. Now, if I cross this, anything less than this, there are now 2 possible dots, 0 or 2. And this is cumulative. You see, cumulative, so you have to keep adding up. So add up. 5/10, 3/10. And then if x goes here, then anything less than x, now I have 3 dots. So I have to add these 3 probabilities. Again, keyword is cumulative, so you have to keep adding up probabilities. So what do you get? Always begin from 0, and then increase, 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 and end up with 1. So if you calculate, you're going to get this. Always begin from 0, end at 1. Here's another visualization of the same thing. This is horizontal tabular form. This is vertical tabular form. I hope it's the same thing. And as for keep adding up probabilities, it's the same thing. Let's see. No, that's not that important. Or piecewise function expression. Now, the graph. So this is CDF, and this is PMF. Always start from 0. Anything less than this x, that's impossible. There's no dot. Now, once I cross 0, probability just shoots up because now it's possible to consider this red. So this jump is same as this probability mass from 0 to 0.5. That jump corresponds to the first addition. Next jump is the second dot. If I cross 2, then anything less than x, I have now 2 dots, red and green now. Red was there before. Now I have green, so that jump is this green. 3/10 is added. Cumulative, so 3/10 is added. And then another jump here, from here, 2/10 is added. 2/10 is added. So we end up with a step from 0 to 1. And then we have jump, 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 which corresponds to probability mass, red, green, blue for these. That's how mass function and distribution function, that's how PMF and CDF are related. I guess we're going to need more example problems like these. And yes, we'll do that in the next video. See you soon.